Welcome to our final section on conic sections. We've discussed circles, ellipses, and parabolas so far. And I think that these all had an air of familiarity. We all know circles, and we had already studied parabolas. And ellipses were just simple generalizations of circles. Hyperbolas, however, are something rather different. Let's look at their formula. They're going to be things of the form x minus a squared over c squared minus y minus b squared over d squared, or I can put the minus sign on the x's instead of the y's. And these will, as was the case with ellipses, will be set equal to 1. So let's recall how hyperbolas are generated from the conic sections. This was the case in which, when I intersected a plane with this double-sided cone, I struck both of them. And I told you that you get a picture with two curves that are linked together, one corresponding for each of the two cones you intersect. So what are the roles of the variables here? So A and B denotes, as usual, the center. And then C and D describe the shape of the hyperbola. So let's look at an example, and I'd like to plot this to give us a sense of how to understand hyperbolas. So if I have x squared minus y squared equals 1, then in this case, I'm looking at a and b are 0 and c and d are 1. So a very simple example compared to what we could do. So let's think about some points that are on here. So if y is equal to 0, then I need to take x to be plus or minus 1. So plotting a few points to get a lay of the land would give me that x is 1, y is 0 is on it, and x has minus 1, y is 0 is on it. Let's think about some other points. How about if y is equal to 1? That tells me that x needs to be equal to plus and minus square root of 2, which is, something like plus and minus 1.4. This is on there. And now let's try maybe x is equal to 2. Then this tells me that y should be equal to plus and minus square root of 3. Whoops, not there. 2, something like that. Right, so here I'm using the approximation. Square root of 3 is something like 1.7. So I can see that the picture is going to be something like this. Like that, and the same thing over here. So I can consider now, is there some other sort of structure to this parabola that I'm not seeing? And the answer is yes, that there is an asymptotic behavior to these types of curves. In fact, I can almost see it from this picture. That there's a pair of lines that this hyperbola is tending towards. And this can be very helpful when you don't necessarily want to plot every point for your hyperbola. So how do I compute these asymptotes? Well, if I'm in this first case, which is what I'll focus on, this has asymptotes with slopes plus and minus d over c. So the asymptotic curves are like y equals plus and minus d over c times x, which makes sense. I mean, they're not just up and down or left and right. They're diagonal. They're lines in the plane. So this can be useful as a tool to help us plot. So as a final example where we'll use this in an important way, we'll consider x plus 2 squared over 9 minus y squared equals 1. So what are some points that are on this? So let's see here. If y is equal to 0, then I need x plus 2 squared to be equal to 9. So x plus 2 should be equal to plus and minus 3. So x should be equal to negative 5 and positive 3. So x is 3, y is 0. I have this. And what else can I tell? Well, this is going to have asymptotes of plus and minus d over c. So in this case, d is equal to 1, and c is equal to the square root of 9, so 3. So my asymptotes will look like y equals plus and minus 1/3 x. So roughly speaking, they'll look something like this. Here's the one corresponding to positive 1/3. And then here's corresponding to negative 1/3. So now we can use these as a guide for our parabola, or hyperbola. So our sketch will look something like this. Ah, yes. So actually, this will be at 1. That was my mistake, not at 3. Sorry about that. Yeah, I made a little algebra mistake here. This should be minus 5 and 1. So, and we can check that that makes sense by looking at where the center of this hyperbola is. It's at minus 2, 0. So this distance here is 3, which should be the same as this distance here to 3. So in order to effectively plot the hyperbolas, you really want to use 3 things. You want to, of course, plug in maybe a point or two to get where you start. You maybe want to use the center to find, to make sure you're symmetric about the center. And then using the asymptotes can give you the kind of structure you need to really flesh out your plot. Now, for the CLEP exam, you'll typically be doing these types of computations without a calculator. So it's difficult perhaps to do some of the calculations if you're not already familiar with the concepts. So I recommend looking at our reading list and also working at the problems I've assigned that discuss these types of conic sections.